So the ultimate source of energy on Earth is the sun. And in the most basic sense, the sun emits solar radiation and it strikes the Earth. And as the planet warms, it emits radiation back towards the atmosphere. The types of energy radiated from the sun and the Earth, they're very different, and we've talked about those before. Because the sun is very hot, most of the radiation energy is in the form of this high energy or visible radiation and also ultraviolet radiation. That's also known as visible and ultraviolet light. When the radiation strikes Earth, the planet warms and radiates energy. Earth is not nearly as hot as the sun, of course, so it emits most of its energy in infrared radiation, also known as infrared light. We cannot see infrared radiation, but we can feel it being emitted from warm surfaces like the heat as it radiates off of the asphalt on the road, when the day is warm. The differences in the types of radiation emitted by the sun and the earth, in combination with process that occurs in the actual atmosphere, cause the planet to warm. So using this diagram, we can kind of walk you through each step of the process here. So as radiation from the sun travels towards Earth, about 1/3 of the radiation is reflected back into outer space. And although some ultraviolet radiation is absorbed by the ozone layer in the stratosphere, the remaining ultraviolet radiation, as well as visible light, easily passes through our atmosphere. And once it passes through the atmosphere, the solar radiation strikes the clouds on the surface of Earth. Some of this radiation is reflected from the surface of the planet, and so it bounces back into space again. The remaining radiation is absorbed by clouds and the surface of Earth, which, becoming warmer and begins to emit this low energy infrared radiation back to the atmosphere. So unlike ultraviolet and visible radiation, infrared radiation does not easily pass through the atmosphere. It is absorbed by gases, which is what causes these gases to actually warm. The warmed gases, they emit infrared radiation out into space and back into the Earth's surface again. So this infrared radiation that is emitted towards Earth causes the Earth's surface to become even warmer. And the absorption of infrared radiation by atmospheric gases, it's basically reiterating this energy back towards Earth, and essentially that's the greenhouse effect. And the greenhouse effect gets its name from the idea that solar radiation causes a gardener's greenhouse to become very warm. However, the process by which actual greenhouses are warmed by the sun involves glass windows holding their heat, whereas the process by which Earth is warmed involves greenhouse gases radiating infrared energy back towards the surface of the actual planet. So in the sun-Earth heating system, the net flux of energy is zero. The inputs of energy of Earth are equal to the outputs of energy of Earth, I guess is what I'm trying to say. So over this long term, thousands or millions of years, the system has been at a steady state. However, on a shorter term, over years and decades, the inputs have been slightly higher or lower than the outputs. And these factors are short-term fluctuations. So we've talked about certain gases in the atmosphere that can absorb infrared radiation, and it can be emitted by the surface of the planet and radiate much of that back towards the surface. We have also seen that gases in the atmosphere that absorb infrared radiation, they're known as greenhouse gases. The two most common gases in the atmosphere are nitrogen and oxygen. They compose 99% of the atmosphere. That's N2 and O2. So because these two gases do not absorb infrared radiation, they are not greenhouse gases and do not contribute to the warming of Earth. This means that greenhouse gases make up a very small fraction of the atmosphere, and the most common greenhouse gas is water vapor, H2O. Water vapor absorbs more infrared radiation from Earth than any other compound, and although the molecule of water vapor does not persist nearly as long as other greenhouse gases, other important greenhouse gases can stay in the atmosphere for a very long time. They're like carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and also ozone, our famous O3. You know, all of these gases, they've been a part of the atmosphere for millions of years, and they've kept Earth warm enough, in order for it to be a habitat for us. So in the case of ozone, we've seen that the effects of Earth, they can be very diverse. And ozone in the stratosphere is beneficial because it filters out harmful ultraviolet radiation. But in opposite of that, ozone in the troposphere, in the lower levels of the atmosphere, they act as a greenhouse gas, and so they can increase warming of Earth. It is also air pollution in the lower troposphere because it causes damage to plants, human respiratory systems, and such. There's also another type of greenhouse gas, chlorofluorocarbons, which we've talked about before, CFCs. And they do not exist naturally. It occurs in the atmosphere exclusively due to production of CFCs by humans. I think we've talked about before that CFCs, they've contributed to a hole in the ozone layer over Antarctica. And we commonly think of the greenhouse effect as detrimental to our environment, but without any greenhouse gases, the average temperature of Earth would be negative 18 degrees Celsius, that's 0 degrees Fahrenheit, instead of its current average temperature, which is 14 degrees C, and that's about 57 degrees Fahrenheit. So concern about the danger of greenhouse gases is really based upon the understanding that an increase in the concentration of these gases has occurred just due to human activity. So that can cause the planet to warm more than usual. The contribution of each gas to global warming depends on the part of its greenhouse warming potential. So the greenhouse warming potential of a gas, that estimates how much a molecule of any compound can contribute to global warming over a period of like 100 years relative to the molecule, like carbon dioxide. So in calculating this potential, scientists consider the amount of infrared energy that a given gas can absorb and how long a molecule of the gas can persist in the atmosphere. Because greenhouse gases can differ a great deal in those two factors, greenhouse warming potentials, they span like a wide range of values. For example, I think water vapor has a lower potential compared to that of carbon dioxide. And we actually have a table for that. So this table shows the global warming potential for 5 different common greenhouse gases. Compared with carbon dioxide, the greenhouse warming potential is 25 times higher for methane, nearly 300 times higher than that of nitrous acid, and up to 13,000 times higher for chlorofluorocarbons. So the effect of each greenhouse gas depends on both its warming potential and its concentration in the atmosphere. Although carbon dioxide has a relatively low warming potential, it is much more abundant than most of the other greenhouse gases, except for water vapor, that is. It can have a concentration similar to carbon dioxide too, by the way. While human activity appears to have little effect on the amount of water in the atmosphere, it's caused a substantial increase in the amount of other greenhouse gases. So among these, carbon dioxide remains the greatest contributor to the greenhouse effect because its concentration is much higher than pretty much all the others. As a result, scientists and policymakers focus their efforts on ways to reduce carbon dioxide in the atmosphere. Makes sense? Yeah. So, given with what we know about greenhouse gases and how they work, and the concentrations of these gases and how much infrared energy each can absorb, we can basically understand the concentrations of greenhouse gases and can contribute global warming to the increase in them historically. And a lot of that has to do with the radiation part too. So, the production of new greenhouse gases that can make their way into the atmosphere, like the CFCs, that should cause an increase in absorption of infrared radiation in the atmosphere and just continue to create the planet, to warm the planet as we invent these new things. So I've alluded to this before that greenhouse gases, they're both natural and anthropogenic. We've seen that greenhouse gases include a variety of things like water vapor, carbon dioxide, methane, nitrous oxide, and CFCs. And these gases have natural and, of course, human sources. And so reviewing the different sources of these gases can help us basically get a ranking system of the different types of things that humans are doing and where they're coming from. So some of the greenhouse gases are produced from a natural source, of course. They include things like volcanic eruptions, decomposition, digestion, denitrification, evaporation, and evapotranspiration, all things that sometimes we could not live without, per se. So I just want to hit on each of these real quickly. So like volcanic eruptions, like if you remember the eruption of 1991 that was in the Philippines, that volcanic eruption that sent like millions of tons of ash into the atmosphere, where it can absorb this incoming solar radiation and radiate it back into space and cause the Earth to become cool. So over the scale of geological time, volcanic eruptions, they can add a significant amount of carbon dioxide to the atmosphere. Other gases that are in large quantities, like ash, during these volcanic eruptions, they also can be important because short term, they do have climate effects. A volcanic eruption emits a large quantity of ash into the atmosphere, and ash reflects the oncoming solar radiation. And it has a cooling effect that can change things. Decomposition and digestion, all right, so when decomposition occurs, it's usually under some high oxygenated condition. So dead organic matter is ultimately converted into carbon dioxide when it decomposes. We've seen a lot of this before. We've talked about it in like the landfill section. Basically, this decomposition produces a lot of methane, and there's just not enough oxygen available to produce carbon dioxide. So the methane is released. This is a common occurrence in mostly, a lot of wetlands too, because plants and animals, they decompose in these low oxygen environments. Also kind of contributes to the funny smell of wetlands. They are the largest source of methane on the actual planet right now. Methane production, it's also similar to what occurs when animals digest plant matter. They consume a significant quantity of wood and grain, including things like termites or grazing antelopes. They require gut bacteria to digest plant material. So because the digestion occurs in this animal's gut, the bacteria do not have access to oxygen, and methane is produced as a byproduct. A single termite colony can contain more than 1 million termites, and termites are abundant throughout the world, especially in the tropics. And so this presents a large natural source of methane, and you can't just blame it all on cows these days. Denitrification, where nitrous oxide, N2O, is a natural component of the nitrogen cycle, and we've talked about that before. So it's produced through a process of denitrification, and denitrification occurs in low oxygen environments inside of soils, usually wet soils, and at the bottom of wetlands, again, even lakes and oceans as well. So in these environments, nitrate is converted to nitrous oxide, which then enters the atmosphere as a very powerful greenhouse gas. Evaporation and evapotranspiration, as we've stated earlier, water vapor is the most abundant greenhouse gas in the atmosphere, and it's the greatest natural contributor to global warming. So we can examine the role of water vapor deeply in our hydraulic cycle, but water vapor is produced when liquid water from land or any other water body evaporates by the evapotranspiration process, and even from the transpiration process inside of plants. So because the amount of evaporation into water vapor really varies based on climate and everything that's there, just regionally everything that's there, the amount of water vapor in the atmosphere varies greatly around the planet.